Everybody, today we want to continue our discussion of the evolution of atomic theory, and last time we left off with Thomson's model. Now remember, through that cathode ray tube experiment, Thomson was able to develop his plum pudding model of the atom, in which he had a solid sphere atom with negatively charged electrons embedded in a positively charged stuff, or a positively charged pudding. And this solved the problems we had with Dalton's model, because now we had a way for atoms to stick together to form chemical bonds. So our next scientist, Ernest Rutherford, spent most of his time, his primary work was in radiation. And he thought that radiation could be an interesting tool in order to investigate the internal structure of the atom. And he chose to use alpha particles. Alpha particles are relatively massive particles compared to many others and have a positive charge. And so what Rutherford thought is, by looking at the deflection of these particles as they pass through a surface, we can then draw some conclusions about that internal structure of the atom. All right, and you can see in the picture here that Rutherford used a thin sheet of gold foil. All right, now gold was used because it is extremely malleable, and so we can bend and shape this gold foil till it's so thin that you can just about see through it. And so it was believed that this foil was in 1 atom thick. However, it turns out now, with modern techniques, we can determine it's actually several hundred atoms thick. So Rutherford, he fired these alpha particles at this thin sheet of gold foil and looked at how they scattered, and using probability was able to determine several things about the atom. Okay, and so this led him to develop what we refer to as the nuclear model, which is a little bit more familiar when we tend to think about an atom nowadays. Now let's look quickly at a little bit of a video with a little more information about his setup.
At the time he carried out the experiment, the atom was thought to be a blob of positive charge with negative electrons embedded inside it. Now, Rutherford set up an experiment to direct a beam of alpha particles, which he knew to be heavy, positively charged particles, and we now know to be the nuclei of helium atoms, through a very thin gold foil. The brass can in the center of the picture contains a small americium-241 source producing alpha particles. Most of the particles are absorbed in the brass. There is a small opening producing a beam of alpha particles. They pass through a gold foil, which is about 1.5 microns in thickness, and they are then detected by one of the 2 detectors set up behind the foil. One of the detectors counts particles going straight ahead, which is the majority, and we count a rate of between 1 and 2,000 per second. The second counter, we can move to measure the scattering rate as a function of angle. Now, the experiment that he and his colleagues carried out was very laborious. It involved them sitting for hours in a dark room, holding a tiny fluorescent screen and looking just by eye for flashes of light on the screen. We've replicated that with modern detector technology. In its current position behind the foil, it will measure 1 count every few seconds. As Rutherford deduced, most of the gold atom's empty space, so the alpha particle just goes straight through, doesn't see anything, and goes through in a straight line. Occasionally, one of the particles will come close enough to the nucleus of the gold atom that it will be deflected by the electric field from the positive nucleus. If it comes at a glancing blow, it will be deflected through a small angle. If it hits it head on, it will just bounce straight back. And it's fascinating, I think, to them that this was telling us something very important that we didn't know about the very deep structure of matter. It showed that the atom had a heavy nucleus with mostly empty space with electrons distributed around it, which is exactly the picture we now have. It was also the start of particle physics. What Rutherford was doing, and what we're doing here, is taking a beam of particles, firing it at a target, looking at the way the particles are scattered, and from that deducing what was going on inside the target.
So now when we consider some of the breakdown just in the basic observations here, all right? So if Thomson's model was correct, Rutherford would have seen a very specific pattern, diffraction pattern, as these alpha particles passed through that Thomson plum pudding model. But that's not what he saw, all right? And so his observations can be kind of broken down into three basic parts. First part, all right, his first observation is that a vast majority of the alpha particles pass straight through the gold foil, completely unaffected. So their path was not at all changed. And so this suggested some very specific things about the internal structure of the atom. These alpha particles weren't hitting anything, right? So some of the alpha particles, Rutherford observed a very slight deflection, okay? They were slightly deflected off as if they had been repelled by something. And then lastly, some of these particles bounce back. And now this particular observation shocked Rutherford the most, and he equated this to a bowling ball fired at a piece of tissue paper, or a cannonball fired at a piece of tissue paper that just bounces back and hits you. And so that, according to the physics at the time, should not have been possible. We should not have been seeing these particles kind of bounce back. So they had to have been coming in contact with something pretty massive and small. So from those observations, we can draw some conclusions. So first off, the fact that most of the alpha particles passed through the gold foil, completely unaffected, through these atoms, Rutherford deduced that the atom is made up of mostly empty space. And this was a big shift in thinking from previous models, and it was a little bit harder to conceptualize. Secondly, all right, if some of the alpha particles were slightly deflected, slightly repelled by something at the center of those atoms, then Rutherford said, all right, well, maybe we're dealing with something that is positively charged. It's going to be small and dense and have a positive charge associated with it. And that positive charge is going to repel the positively charged alpha particles, and we'll see the deflection pattern that we observed. And then lastly, all right, if some of these alpha particles are bouncing back, they have to come in contact with something very, very massive. All right, and so very massive and very small. So from this, we can see that most of the mass of the atom itself is packed into that very tiny, dense nucleus with a positive charge. And that's going to allow these alpha particles to bounce back the way that they came. And so you can see we now starting to develop a model that looks a little bit more like we currently envision an atom. Thanks for listening. Enjoy your day.